Now that we know what a function is in physics, we're going to look at a couple of examples of functions. And specifically, we're going to focus on functions that are called power functions. So we will learn, in total, we're going to learn about two different types of functions. One class will be power functions, and the other will be called exponential functions. So this is the first type or class of functions that we'll study. Imagine you do an experiment where you take a ball and you drop it so that it's in free fall, maybe about 10 meters above the surface of the earth. You do this and you conduct several trials. In each trial, you let the ball fall for a different amount of time and you measure how far down the ball travels. So your independent variable is time, and your dependent variable is distance traveled. And you conduct your experiment, collect the data, you analyze your data, and what you see is here's the relationship, here's the function between time and distance traveled by the ball. Distance, which I'm going to call S, is equal to negative 4.9 meters per second squared times time. Now you do another experiment where, time squared. That would be bad. Okay, now you do another experiment where you go out into the forest and you look at the trees and you examine how the age of a tree depends upon the diameter. So the older the tree, the bigger the diameter. And what you find is that tree age, the time that the tree has been around, so I'll call that T, tree age is equal to 6.5 seconds, and the units here are seconds, meter to the negative 1.5 times the diameter raised to the power of 1.5. Okay. Kind of a weird power there. Now imagine that you go out, so we're going to do a few of these. You do another experiment, and in the next experiment, you let the ball drop again. Again, it's from rest. And in each trial, you let the ball fall for a different amount of time, and you measure at the end of each time period, you measure how fast the ball is going. And what you find is that the speed v is equal to negative 9.8 meters per second squared times the time. Okay, two more to go. In the next experiment, you hold a ball above a spring, and the spring is initially relaxed. You let the ball drop, and then the ball hits the spring, so it falls down, the ball falls, it hits the spring, and it compresses the spring. The experiment you do is you change the initial height, and you see how that impacts the amount of compression, x. And so your dependent variable is x, compression, and the relationship that you find is, let's say, x equals 18 meters to the 1/2, that's the unit, meters to the 1/2, times the square root of height. Okay, and the very last experiment that you do is you take a picture of a golf ball, and the golf ball is initially 1 meter from your phone, and then you look at that picture and you measure how high is the golf ball on your phone. What's the height of the image? And then you take the golf ball and you move it back, so it's 2 meters away from your phone. You take another picture, you measure again, what's the height of the image? And what you find is that the image height, which I'll call h, is equal to 2.4 meters squared over the distance between your camera and the golf ball, d. Now, as it turns out, all of these functions we've written down, every single one is a power function. So I'm going to take each equation and I'm going to rewrite it over on the right side. So I'll write the first one this way. S equals negative 4.9 t squared. I'll write the next one this way. T equals 6.5 times d to the 1.5 power. The next one I'll show as v equals negative 9.8 times t to the 1. So in each case, you notice I'm dropping the units because we're not too concerned with units at this time. And I'm also writing in every single exponent. So I've just written in the 1, which is the exponent for t. The next one we could write as x equals 18 h to the 1/2. And then finally, h is equal to 2.4 times, let's see, d to the negative 1. Because whenever there's something in the denominator, we could bring it into the numerator by making its exponent negative. Now, in each case, in all of these equations, there is a single form that they follow. Every single equation has the dependent variable isolated on the left side. Now, whether it's the left or the right doesn't matter. The point is that the dependent variable is isolated. It's all alone by itself on one of the sides of the equation. Then, on the other side, we have a constant, right, for negative 4.9, 6.5, negative 9.8, 18, 2.4. We have a constant multiplied by the independent variable, time, distance, time, height. This was diameter, and this was distance. And then the independent variable is raised to some power, right? 2, 1.5, 1, half, negative 1. The power can be any number. So here's the general form for a power relationship or a power function. The dependent variable, whatever it is equal to a constant, which we'll call k, constant k times the independent variable raised to a power n. So that's it. This is a power function. Any equation that has this form is considered a power function, and it doesn't matter what the dependent variable is, what the independent variable is. Remember that k is a constant and n is a constant. So we could stipulate where k and n are constants. Constants. They're ants, not uncles. Ants, no. Bugs, insects. Okay, so that's what we're going to learn about power functions today in this video.